Hi guys, welcome to one more video on linear integrated circuits. So here we are looking at the applications of Opamp. We are looking at the simulations of Astable multivibrator using Opamp. We know that of course this is a circuit of an Astable multivibrator. As you know that R1, R2 and the Opamp will form the inverting Smith trigger, and there is a feedback given from output to the inverting terminal of the Opamp using R and C. So we have studied in the previous video that if the capacitor voltage exceeds VTH, the output is changing from plus Vsat to minus Vsat. If your capacitor voltage goes below VTL, output again goes back to uh, plus Vsat. So this way, how it is keep on changing from plus Vsat to minus Vsat simultaneously without any stoppage. That's why it is called as an astable multivibrator. It doesn't require any input voltage. Now let us have a look at the design part of it using the equation T on is equal to RC ln of 1 plus beta by 1 minus beta, where beta is given by R1 divided by R1 plus R2. So care should be taken that while calculating beta value, so this is as per the location of the resistor. If R1 is connected to non-inverting and ground, then only you should take this as R1 by R1 plus R2. Otherwise, appropriately you have to consider. Now in this design part, which is type 1, we have been given specification of R1 is equal to 1K, R2 is equal to 2 kilo ohms, R is 1K and C is equal to 0.1 microfarad. So we are asked to estimate the frequency and of course the on time and off time. Since the values of R1 and R2 both are same, the beta becomes 0.5. By substituting that beta in this expression and the given values of timing resistor and timing capacitor, the on time and off time comes out to be 109 microsecond, which happens to be a frequency of 4.58 kilohertz. So you can actually do the simulation of this particular example and try to verify what is the oscillating frequency and the on time and off time. So let me do that. So this is the simulation. We have actually rigged up the circuit. You can see one more thing. So in this, the on time off time is independent of the supply voltage. So in this case, we have taken the supply voltage as plus 12 and minus 12. So we are using an Opamp which is there built in this LT spice, that is LT1007A, and we have the values of R1, R2 as 1 kilo ohm each, and the timing ratio is also 1 k, and the C value is 0.1 microfarad. For these specifications, we are supposed to get a time period on time and off time as 109 microsecond with a frequency as 4.58 kilohertz. So let us run this program, try to find out what is the output waveform. So let us see the output here. Now you can see it is keep on oscillating, and we can also see how does the capacitor voltage changes. Carefully look at now the capacitor voltage is going up to VTH and VTL. You can see. So let us first verify the on time and off time. Let me just see what is the on time here. Now it is approximately, we are supposed to get 109, so we are getting close to this is 107 microsecond. So this is we can also actually find the frequency by moving this to one cycle. I can just move it close to one cycle. Now you can see now the frequency is 4.51 kilohertz. We are expecting the frequency of 4.58, so we are getting very close to that frequency. And you can see the capacitor voltage will be charging up to beta VCC and minus beta VCC. We can actually find out what is the value of plus Vsat and minus Vsat. Even though VCC is 12 volt and minus 12 volt, actually Vsat is 10.25. The minus Vsat is, you can have a look at it, is minus 10.13. So this is minus Vsat, this is plus Vsat. So this way we can actually find out what is the capacitor voltage. The capacitor voltage will go up to beta times VCC, so Vsat. So beta is actually 0.5. The Vsat is 10.25 something. Now the capacitor voltage will be charging up to 5.6. You can just have a look at this voltage. You can see it is this is your first cursor. You can see it is close to 5.16 volts. So this is plus beta Vsat, and similarly we can find minus beta Vsat, which is minus 5.13. So this is the capacitor voltage VTH and VTL. Similarly, we can change the values of R and C here. Now let me keep the values of R1 and R same. So if I just modify the value of R2 and C, we are supposed to get the frequency as 42 kilohertz. Let us do the same here. So let me change the R2 value to 10 kilo ohms. Now let me make this 10k, and the value of C happens to be 0.01, 0.01 microfarad. So let us run this. We are supposed to get a frequency of 42 kilohertz. Surprisingly, you can see you're not getting a proper waveform. Now, why you're not getting a proper waveform in this particular case is, it is purely because this op-amp has got a limitation in terms of its operating frequency. If we use a better op-amp which has got its slew rate very high, then we can get a proper square wave. Now you can see it is taking longer time to go from minus Vsat to plus Vsat. By that time your capacitor is charged. So that's why it is not happening. You're not getting a proper square wave. So let me change this the op-amp from these two different one. So let me just look for a different op-amp family, which is a better one. You can see it is ultra low noise, high precision, and high speed operational op-amp. So let us just use this and try to. So now you can see you are supposed to connect the non-inverting. Let me select this and then make the mirror image and then rotate it. Let me make it. This is fine now. Now let me delete this and close this. Now we are trying to use a op-amp which is having a better characteristics in terms of slew rate and its high frequency. Now you can see it is better. Now you can see we can able to get at least let me just stop this and try to find out. Let me slightly increase the frequency of this operation. Let me make this 0.1. Now you can see we're getting this with this as 0.01. We are not getting a proper waveform. It is purely because the output is unable to make a transition from plus Vsat to minus Vsat. So I think even with this as 0.01, so let us try to reduce the input voltage and try to get the proper waveform. So let me just make the output voltage for the plus Vsat as just only 5, and here also it is 5 here. So this 5 with negative voltage make it minus VCC. Now let me save this and run. Now still this op-amp with this frequency is not suitable for operation. Now you can see it is having a output transition, but it is not a good op-amp because it is still not suitable for this operation. So let me just reduce this C2 point. Let me increase this C by 10 times, and you can see now we are getting. So this entire analysis, what we are trying to do is, when I did it for a higher frequency, which is like 42 kilohertz, it's not coming properly because the op-amp is not responding to this high frequency. If you want to achieve a higher frequency using op-amp, you have to have op-amp of very good quality having a very good slew rate. So this is one of the limitation of the op-amp for generation of the square wave. So whereas in case of 555 timer, we could able to generate the frequency in terms of 50 kilohertz suitably without any problem. Now here you can see for higher frequencies we have the problem in terms of selecting the op-amp. Let us see in more design how can we do it. So here in second type, we are supposed to get a time period of 1 millisecond on time. The values of R is given as 2.2k. This is beta is equal to 0.2. Since beta is given as 0.2, so we have this 0.2 is equal to R1 by R1 plus R2. When we have only one equation, two unknowns, you cannot find both of them. So we'll assume the value of R1, R2 comes out to be 40K, and C value is 1.12 microfarad. So this will end up with a time period of 1 millisecond on-off time, and with R is equal to so and so. Let us just redo the same thing for this. So we need to have this R is equal to 2.2 kilo ohms, and this C is 1.12 microfarad. The values of R1 was found out to be 10K, and the value of R2 calculated to be 40K. We are supposed to get an on time of 1 millisecond. Let me run this now. Now since it is simulated for a very small time, let me just make it for 5 milliseconds. And let me run it now. Now you can see we are having this. If I forget about this, now you can see it is going up to. You can actually find what is the time period now here. So this is actually, you can see the time is exactly 971 microsecond, which is very close to 1 millisecond. You can actually slightly move this. So this is very close to, you can see it is 969 microsecond, which is close to 1000 microsecond. So this way we can able to get the oscillations of desired frequency time period. The capacitor is charging up to beta times Vsat. In this case, Vsat is pretty less now, so it is close to 3.1 volts because VCC is 5 volt. So Vsat is not usually equal to Vsat. It will be around 80 to 90% of VCC. So we can also do one more type of design where we are assuming a frequency of 500 Hertz. Duty cycle is 50%. The value of C is assumed to be is given as 0.1 microfarad. The value of beta is given as 0.2. We are asked to find out the values of the resistors R1, R2, and R. So those values are found out to be so and so. Let me just connect these values and verify the same. So R1 is 16. Okay, let me just connect the same values. This R is 16.67K. The value of C is 0.1 micro, and let us see how much is the value of R1, R2. R2 is 10K and R1 is 4.28. So R2 is 10K. This is 4.28. We are supposed to get a frequency of 500 Hertz with 50% duty cycle is what is expected. So this is 16, it is 16.15. I can verify, is it 16.15? And this is the 16.15. Let me run this now. Save it, run. You can see the time period is pretty less. Let me just make this. Let me zoom this. Here it is taken as, this should be K. This should be K. Now let me save it and run. Now you can see this is the proper waveform. The expected duty cycle is 50%. The frequency is, let us verify the frequency. Frequency expected was 500 Hertz. You can see it is close to 600 Hertz. So if you can properly place the cursors exactly over there, now you can see the frequencies close to 500 kilohertz. It is around 590 kilohertz. The on time and off time is as per the design. So this way we can do the design by changing the values of R1, R2, R as well as C to get the desired frequency of oscillation.